Thank you for the introduction. Thanks also to the organizers for inviting me. So I'll be talking about quantile estimation in streams, and this is joint work with Meghal Gupta and Hongshin Wu, who are both also students here. Okay, so let me start by just describing the problem at hand. So this is a streaming problem, so we're going to receive a stream of numbers one by one as an input, and our goal is going to be to keep as low memory as possible throughout the stream. So more specifically, we have some universe of size u. If the inputs are sort of integers that are machine words, you can think of this as like 2 to the 64 or something. Basically, there's some universe of size u, and we're getting inputs from 1 through u. And we basically get a stream of length n. And at the end of this stream, I'm going to basically ask you for the rank of some element x, or some number x in the universe. And the rank of a number is just the number of stream elements that are less than or equal to that number. And sort of equivalently, instead of asking for the rank of an element, it turns out to be equivalent to also receive the rank as a query. And then you have to tell me an element of the stream that was at approximately that rank. So you can't do this exactly. If you had to give the exact rank of an element, you just need to remember the whole stream. So we asked that the rank is accurate up to an error of epsilon n. So maybe I'll give a quick, just short example. So if this is the stream, just these 6 numbers, you don't shout out the rank of 3. You only have to be approximately right. 1 is not approximately right. Try again. 4-ish is right. The answer is 4, because you can see there are 4 numbers that are less than 3 in the stream. I would also have accepted 3 or 5. Okay, does everyone understand the problem at hand? Move on. Okay, great. So, right. Okay, so I think this problem is of theoretical interest, but for those of you who care about applications, I have some applications of this as well. So maybe the most, what one possible use is if you want to estimate like the reliability of a system. Like if you have maybe a bunch of servers and each of those servers has some latency, maybe you want to know how slow like the slowest 1% of the servers are, the slowest 10% are. And you can use a quantile estimate to do that. Right. Other things, if you want to do user analytics of any sort, if you want to approximate the median or like whatever quantile you want of some of the views of video or things like that, this is all like common stuff like subroutines you might need. You can also use a sketch for that. And in practice, there are many libraries that actually implement sort of the best current algorithms for a quantile sketch. Sorry, was there a question?
So this is adversarial order?
Yeah, adversarial order. The stream is adversarial.
I just think to be more like the random case, maybe?
Yeah. I guess the algorithm I'll talk about is deterministic. So I guess if you ask for a random stream, you need to start talking about failure probabilities and such. I'm not aware of any work that's been done in the random order case. Any more questions? Okay, yeah. So in practice, there are many libraries that implement quantile sketches. You can see some examples here. Right. Oh, I clicked twice. Okay, so let me just talk about the history of results. So the first algorithm that was proposed for quantile sketches was called the MRL sketch. That's by Manku, Rajagopalan, and Lindsay. This is back in 1998, and they showed that you can make a quantile sketch that uses epsilon inverse times log squared of n words. So here I use the word word to mean basically the maximum of log n and log u bits. So we're assuming that you're doing this whole thing on a machine where like the machine word can store the number n and can store the number u, or it can store numbers up to n or u. Right, so the space of the MRL sketch was epsilon inverse times log squared n, and this was improved 3 years later by Greenwald-Khanna in 2001 to epsilon inverse times log n. So they chopped off a log factor from this. And both of these algorithms are what we call comparison-based. So by comparison-based algorithm, I mean that when you receive a stream element, like the only things you're allowed to do to it are compared to other stream elements. Like we're not using the bits of the numbers themselves or their identities in any way. And it turns out, and then you can store those elements, but all you can do with the stored elements is compare them to later elements. So it turns out that the GK sketch is actually the best you can do for any deterministic comparison-based algorithm. So to do any better than that, we'll sort of need to look beyond the comparison-based model to try to find better algorithms. Okay, so sort of in a separate direction, the Q-digest algorithm in 2004 achieves a space complexity of epsilon inverse times log u. So this is not a comparison-based algorithm, and the performance is kind of incomparable to the GK sketch. It depends on whether n or u is bigger. And then for a while, there was not much progress on this problem until 2016, when Karnan, Lang, and Liberty developed a randomized sketch that gets for any constant failure probability inverse epsilon words of space. Right? But it's more precisely that the space complexity is epsilon inverse times log 1 over delta, where delta is a failure probability. So finally, in this talk, I'm going to talk about a new algorithm that can get of epsilon inverse words deterministically. And this turns out to be optimal, and I'll talk more about lower bounds later. Okay, so maybe next I'll just start describing the algorithm. I'll describe like a slightly simplified version of the algorithm that gets basically all the way there. Yeah.
You're assuming the elements are actually integers from 1 to u?
They can be drawn from any fixed universe, right? Because you can biject any fixed universe to 1 through u. You need to know what the possible set of elements was in advance. You can't I guess the elements are not can't be abstract elements of some set that you can compare, but you can only, which I think, if you can store an element, I think that's probably the most reasonable model anyway. Any more questions?
You also need to know the stream length or an approximation stream in advance.
Yes, I didn't talk about that. For what I'm going to describe, I'm going to describe it as if we knew n in advance, but it turns out that you don't actually need to know the stream length in advance. You can get an algorithm that does this, that changes n adaptively. Yeah.
So have you adaptively changing when the new element is coming in the stream? Then can you adapt to it?
I don't think our algorithm can deal with u adaptively changing. I guess it's not super clear what. Yeah, I'm not sure. I haven't thought about it. I think there might be ways, but I don't know of any. So I'm not going to say anything on the record. Okay. Okay. So I'm going to start by describing the Q-digest sketch that I mentioned earlier. This is the one that gets epsilon inverse times log u words of memory. Okay, so imagine that we have this big binary tree on the entire universe of size u, right? It's a massive binary tree. Obviously, we can't store the whole binary tree, but just imagine it in your head. And okay, so we'll give each node of this binary tree, it's a balanced binary tree. Each node will be some sub-interval of the stream elements. So you can see here, okay, the point here. You can see here that this node is okay, whatever. This node is the interval 3, 4 because its children span from 3 to 4. And basically what we're going to do is as we receive the stream, we're going to put elements into nodes. And we're only going to put elements of the stream into nodes whose interval contains that number. But we'll have the caveat that each node has some capacity alpha. And I've picked this value of alpha. It'll become clear why I've chosen it later. Okay, right, so how do we deal with insertion? So upon getting each stream element, we'll sort of look at the nodes that might contain it. Right? These are some paths going down the tree. And we'll just insert the element into the node the highest possible node that's not yet full at its capacity. So I guess the leaves don't have any capacity here because you might overfloat the leaf, but every node above the leaves has this capacity alpha. Okay, so let's run through an example again. This is the same stream as before. Right, so x1 is 3. We can just put it at the top because the top node is still empty. Similarly, x2 can also go at the top. Any element can go in the top node. Okay, now x3 is 2. It can't go in the top node because the top node is now full. We have the capacity of 2. So instead, we're going to go 1 vertex down from the top node, and we're going to put it in this 1, 2 node. Okay, x4 is now 4. That has to go on the other side, right? It's in the interval 3, 4, not 1, 2. X5 similarly goes in with x3. And now x6, you notice that node is now full with both x3 and x5. So we'll put it just at the very bottom here. Okay, and finally, now that we've inserted all these nodes, so right, we're not actually going to store the elements that each node stores. Again, that would be as much as storing the whole stream. So we're just going to remember for each node, how many elements of the stream did it have. Okay, so instead of these, we're just going to replace it with a bunch of counts. Okay, does everyone understand, like, I haven't talked yet about how this relates to quantiles at all, but does everyone understand how this, like, data structure works? Okay. Let's move on to now how we can answer rank queries using this data structure. Right, so we have this thing, like, and let's assume that we get a query of x equals 3 like we did before. Right, we can look at the nodes. We can see which nodes like might have had numbers that were less than 3. Right, okay, so some of these intervals, we know that 1, 1, 2, 2, and 1, 2, these are all entirely less than 3. So all the elements that we stored there must have been less than 3. So our algorithm is just going to be like, take all those intervals that are strictly less than 3, and we'll just add them all up. Right, so I've marked them in blue here. We'll add up the weights of everything in blue. And you'll see that we got, if you add up 1 plus 2, we'll get a count of 3. What we wanted was a count of 4. So, right, which elements might we have missed in this count? Right, there are some nodes that contain both elements that were less than x and also elements that were greater than x. And for those, like, we didn't know whether to count them or not, so we just didn't count them here. But all those nodes, like, they must contain x, so they must be like strict ancestors of x in the tree. So if you like draw the path up from the queried node, like those are the only nodes that might contain elements that you can miss. Right? Okay. So how many elements in total could we have missed in this rank query? Well, they're log u ancestors because this is a big binary tree of height log u. And so each of them have at most alpha elements that they contain. So the total error in the rank is just alpha times log u at most. And we picked alpha, so this is at most epsilon n. Okay, does that make sense to everyone? Are there any questions? Okay. Yeah, so I'm going to describe how to store this better than u bits, right, in the next slide. Okay, so how do we store this big tree? Obviously, we don't want u bits of information. So instead, it should be a pretty sparse tree, right? There are most n like full nodes in this whole thing. So we want to store basically a list of all of the non-empty nodes, and we want to store what their counts are. So instead of storing the whole tree, we'll just like keep the location of each non-empty node and its count. Okay, so first let's bound the number of non-empty nodes. Right, so okay, a priori, I guess you might have n nodes each with a count of 1. But actually, this can't happen, right? Because if you have a node that is non-empty, its parent must have been full. Its parent in the tree must have been full. And because this is a binary tree, the number of non-empty nodes is at most O of the number of parents of non-empty nodes. And the parents of non-empty nodes are all full nodes with alpha elements, so they're at most n over alpha of them. And so in turn, the number of non-empty nodes is also at most n over alpha, which comes out to epsilon inverse times log u. Okay, so how do we store all the nodes? So I said you can just store all their locations, and you can do that. That would take log u bits per node. But you can do a little better than that, right? The nodes that are non-empty, they form this like tree going down. They're all connected to the root vertex. And so you only need to like store the topology of the tree, just the shape of the tree. Like for each node, does it have a left neighbor? Does it have a right neighbor? And so on. And so just to store the shape of a tree, it only takes 1 bit per node of the tree instead of log u bits per node of the tree. Storing the counts is more expensive though, right? We just need to store, as I've described this, we only need to store a number from 1 to alpha. And that's going to be log alpha bits per node. Alpha is roughly n, roughly speaking. So counts are about log n bits per node, which is pretty expensive. So the total storage we get for QDigest is in bits is epsilon inverse times log u times log n. Notice that I've written it in bits instead of words here because it's more precise. Okay, so that's the QDigest algorithm. Does anyone have any questions about QDigest right now? Yeah. If you change the capacity according to the height of the tree. So
they're going to pay like, oh, log u is the maximum length, and so you multiply by that, but you could be like, oh no, I only need to multiply by that.
So the tree needs to have u elements at the bottom. Right, so that's.
I'm I'm talking about the capacity of a different capacity depending on the height.
Oh, a different capacity for a different height, like for the height of each node on the tree. Yeah, we tried things like this. I don't think anything gets better than this.
You could store approximate counts instead of counts, and then I guess go from like log n to log n or something for the counts.
Right. So you could try to do something like that. I guess that has to be inherently randomized. And the Morse counter has like a log 1 over delta term.
I see you want
Right. So you can't do better than KLL that way. Any other questions? Okay. Right. So I guess our goal is just going to be to try to improve on how we do this QDigest sketch. And sort of a natural place to look, right? We have just 1 bit per node to store the list of nodes. So maybe we can improve the count part, right? So we're not directly going to use a Morse counter, but like we will attempt to try to store approximate counts in some way in order to improve the space complexity of this algorithm. Okay. Right. So our basic idea is that we do only want to store approximate counts of each node. We want to basically round them all off to some multiple of something so that we aren't using as much space for each count. Okay, like if you try to do this directly, what happens when you insert an element, when you like process a stream element, you try to increase a count by 1, and then you round it and you're back to your original tree, and you never make any progress this way. So we have to be a little smarter about how we deal with insertions of elements into this data structure. Okay, so that said, like let's imagine some like intermediate stage of this QDigest, right? We have some non-empty nodes. I don't know if the color is super clear. They're a little grayed out. There's some non-empty nodes like marked with C greater than 0. The state of the tree like is some list of non-empty nodes. And let's look at all the children of non-empty nodes. I guess all the empty children of non-empty nodes. Let's call them V1 through Vm. And every time we insert an element into the QDigest tree, we like basically, I'm lying a little. We basically want to increase the count of some Vi by 1. We might actually want to increase the count of its parent if the parent is not yet full. But we can sort of do that in a post-processing step, right? We can always move weight from Vi to its parent. So let's imagine for now that every time we insert, we would just increment a count of some Vi directly. So the basic idea is we're going to, instead of processing the insertions 1 by 1 and adding them into this count, we want to process the insertions in batches. Basically, we'll split up the stream into batches of size alpha, where alpha is the capacity of each node. And we'll process each batch like using a separate data structure. And after each batch, we want to increment the counts of the Vi using that data structure. Yeah. Right. So the reason that the batches are limited to size alpha, as I'm describing it now, is that we don't want to like overfill any of the Vi. Right. If we had more than alpha nodes going into some Vi, we wouldn't know like which children to assign the weight to, the counts to. Okay, so that's going to be like the basic idea here. We want to process the insertions in batches. And now let's talk about, what would we need of such a data structure, basically? If we were doing this batch thing, like what should such a data structure look like? Okay. So basically, we have this batch. It's like sort of like a shorter stream of length alpha instead of length n. And each of the elements in the batch, maps to some Vi, right? We know which Vi it should go to, and that's the only thing we care about for all those elements. We don't care about anything more detailed, like the actual number. So you can think of the batch as consisting just of some copies of V1 through Vm. And what we want out of this data structure is to get approximate counts. We want like C1 prime to Cm prime, which approximate the actual counts which actually occur in the batch. Right? Okay, so what do we need from these approximate counts? Well, let's imagine what happens if you do a rank query on this data structure. It'll basically add up all the things to the left of some point. So a rank query will look something like this. And my point here is that what is the error introduced into the rank query if you replace the count ci with the count ci prime? Well, it's some prefix sum, right? It's like any rank query only counts C1 plus C2 plus up to CK. It doesn't count, like it doesn't add up arbitrary subsets of the counts. It adds up some prefix of the subsets. So the error that you get in the rank query is just like the difference between the sum of C1 through CK and the approximate value. So that means it's enough to just like get an approximation of the sums, right? Because if you have an approximation of the sums, you can subtract them pairwise to get what the approximate counts would want to be there. And how accurate do we need the approximation to be? We need the approximation to be accurate within epsilon times alpha, right? Because these batches have size alpha. Each time you do this, you can accumulate an error of epsilon alpha so that the total error after this whole thing is at most epsilon n. Okay, so just to summarize, we have this batch. We're getting basically this batch consists of elements v1 through vm. And we want at the end of this batch to get an approximation to the number of the stream elements that were like up to vk. So does anyone see where I'm going with this? Is there another binary tree somewhere? What does that mean?
Well, something that stores the prefix sums.
Yeah.
Like a quantile.
Yeah, this is another quantile sketch. Right. So that's sort of the punchline of this algorithm, is that like, asking for C1 plus dot 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 plus CK, that's just asking for the rank of k plus 1, of vk plus 1 in this like smaller stream of size alpha. Right, you have the stream of size alpha, you want the number of instances of v1 through vk in total. That's just asking for the number of stream elements or less than vk plus 1. So basically, we now want to initialize like a smaller quantile sketch for this batch on just the v1 through vm. And the hope now is that like the number m, v1, the number of vi's should be like much less than the original universe size u.
Also, the universe size shrink. The universe size shrink dramatically.
Yeah, exactly.
But you don't have the structure of that universe, though.
Yeah. Okay. So I'm just gonna. That's the next slide, right? So we have this like. Right. We have this. This is the Q digest tree initially. All these VIs have a lot of children and descendants here. Like you can imagine this tree is really big, but only a few of the top nodes are filled. And now, when we when we start processing a batch, we'll create a new Q digest structure on V1 through VM. And this is very much smaller, right? And I'll do the analysis in the next slide. But does everyone understand like essentially what's happening here? Okay, right? So we processed insertions in batches. We use a smaller Q digest, an inner Q digest, to get approximate counts back for the V1 through VM in a way that like the approximation guarantee of these approximate counts kind of lines up with what we want. Okay, so what are the parameters of the inner Q digest? Right. So first of all, what's the stream length? It's just alpha. We'll just upper bound alpha by n coarsely because it's, again, alpha is basically n in log ln. Okay, what's a universe? Right, the universe is a number of VIs. So these are all children of non-empty nodes. And as I mentioned earlier, the number of children of non-empty nodes is at most a constant factor from the number of non-empty nodes. And we said the number of non-empty nodes earlier was epsilon inverse times log u. So it's again the same thing. And finally, the approximation parameter, I said earlier that we wanted to approximate within epsilon alpha still. So we get the same approximation parameter, basically. Right, so how much space does this take? If you recall, it was like, epsilon log n log u bits. And so if you plug in the new parameters to this, basically you'll get epsilon inverse times log n times log u bits, right? This universe size u has shrunk basically by an entire log factor. I'm using this O tilde to hide the polylog epsilons for now. I'll talk about how to get rid of those later. Okay, that's the inner Q digest. We still have to store this outer tree and the counts on the outer tree. But now, the counts are being stored in multiples of epsilon times alpha, right? After getting the counts out of the lower Q digest, we can just sort of round them off. So it stores like basically counts in multiples of epsilon alpha. I'm hiding a few details here. But essentially, these multiples of epsilon alpha, now we're only storing a number basically from 1 to 1 over epsilon. This takes O of log of inverse epsilon bits per node, which we're just going to call O tilde of 1 for now. And so if you recall, the number of nodes, again, was epsilon inverse times log u. So that's how many bits we'll get up to this log factor for the outer Q digest. Right, okay, and let's convert this all to words, our favorite unit. So this log u disappears, this log n disappears. And so we get epsilon inverse times log u words, again, up to polylogs of 1 over epsilon. Okay, does anyone have questions at this point? This is sort of like the main idea of our algorithm, and now I'll describe how to get it even further down. Okay, so first of all, we replaced this one level with a Q digest, but why stop there, right? You can replace the inner Q digest with just another instance of our algorithm. And you can keep doing this. You can do it log star u times. Right, I've been a little sloppy with the epsilons, right? A lot of the places I wrote epsilon, I should have written like epsilon over 2 or something, because we're adding up the errors from the inner Q digest and the outer Q digest. So actually, you'll need to reduce the error parameter by a factor of log star u for each recursive layer. So that means that we're going to lose a factor of log star u in our space complexity. So now, if you do all the bounding, we're going to get another polylog of 1 over epsilon somewhere along the way as well. We're going to end up basically with O tilde of epsilon inverse times log star u words. And I think the log factor is like a log squared of 1 over epsilon or something, though don't quote me on that. Okay, but this is very close to what we want already, right? We wanted O of epsilon inverse, and now we have O tilde of epsilon inverse times log star u, which is basically O tilde 5 epsilon inverse. Okay, so that's sort of the main body of our algorithm. Next, I'll describe I'll vaguely describe some of the modifications we need to push this all the way down. But does anyone have any questions right now before I do that? Yeah.
Is there actually like a 1 over epsilon times log n bits in your algorithm at all, or?
Yes. So the log n bits comes from the lowest layer. Basically, at the bottom layer, you can't do this infinitely many times. At the bottom layer, you'll basically have to store. You'll have u equals epsilon log 1 over epsilon. And you can do a Q digest there, but it's just as efficient to just store the counts directly. But you can't get away from that log n at the lowest layer. Yeah.
I've got some kind of meta question. When you see that, I understand that you might be like, oh, we should be able to shape the log square 1 over epsilon, but what made you believe you could shape the log star?
Okay, so that's actually the easy part, as we'll see. So, okay, maybe the log star comes from sort of just this fact is what the log star comes from. Because the main layers of this recursion are the top and the bottom layers of the recursion. Everything in between, we don't care that much about it. They take up much less space than the top and bottom layers. So basically, instead of giving each one epsilon over log star u, we can give epsilon over 4, and then decrease geometrically from the bottom layer going up. So that part's easy, relatively speaking. The harder thing is this polylog of epsilon inverse. So it's actually kind of annoying. Right. So the main log 1 over epsilon term is from this approximate counts. Right. We still had the approximate counts to precision of epsilon times alpha. And in order to get that down to 1, we'll need a precision of alpha directly. So instead of even storing approximate counts, now we just have to remember for each node, is it full or not? And that's going to have to suffice. Right, and then that error sort of propagates, right? Because our rounding off to epsilon alpha was because the batches had size alpha. So if you're rounding off to epsilon n instead, then the batches will need to have size almost n. More precisely, about n over log u is how big the batches have to be. Right, so the batches are now big, and now when you process an entire batch, you might be overfilling the nodes vi. So instead, when the node vi would get full, you need to know to branch down into a smaller binary, into a subtree of vi at the base level of of the inner Q digest, right? At the inner Q digest, if you know that you're going to fill up VI, you need to then like keep track of how much you would insert into the children of VI in the outer Q digest. Again, this is all very vague. I just mean to give you like a rough idea of how this works. But that's how you get rid of one of the log 1 over epsilon factors. The other one comes from the fact that if you repeat this recursively, you actually only get down to u equals 1 over epsilon times log 1 over epsilon, when you really want to get down all the way to universe size of 1 over epsilon. So to deal with that, actually, the Q digest tree has one tree of height log u. You can split this up into 1 over epsilon trees and have their heights be log epsilon u. And this like basically allows you to bring it all the way down to bring the recursion all the way down to u equals 1 over epsilon. Okay, again, like my point here was just to be like give just the rough ideas of how you can get there. I'm not saying anything formal here. Yeah. Hmm.
And will you be able to now store multiple of them into a single board now that these things are shrinking? Because you don't need to store log n b to log u.
Yeah, you can store basically, yeah. For constant epsilon, like the inner layers, the layers that are not the top one and not like a constant away from the bottom one, you can store them all with with like a sub constant number of words. Any other questions? Okay, so that's the part about reducing the space all the way down to epsilon inverse. And now finally, I'll just talk briefly about lower bounds. So I said I've been saying 1 over epsilon words this whole time. If you do the bounding carefully and all that, you'll get epsilon inverse times log epsilon u plus log epsilon n bits. Okay, so you can ask, is this the best you can do? And there is an easy lower bound. One of these lower bounds is easy. If you give the algorithm just epsilon n copies of a bunch of elements of the universe, you basically have to remember some unordered set of 1 over epsilon elements of the universe. So that's u choose 1 over epsilon, which comes out to about epsilon inverse times log epsilon u bits. So that's like 1/2 of the lower bound. So we asked in our paper if you can get the other half of the lower bound, because it wasn't known. And actually, it's just been proven by a visiting student here at Berkeley. Yichuan Wang showed that actually any deterministic quantile sketch requires like the second term, epsilon inverse times log epsilon n bits. So it turns out the algorithm actually is completely optimal. I've assumed so far that n and u are at least 1 over epsilon. The regime where they're not is like sort of degenerate, so I guess we don't really care about that regime. But anyway, this lower bound shows our algorithm is in fact optimal in the number of bits. And that's all I have. Thank you.
Okay, so I will ask a well-intentioned question. So would you implement this? Is there a simplified version that gets you enough of the way there that you would choose to implement? It seems a little bit fiddly.
Yeah, it is fiddly. I think so we haven't tried implementing because we're not good at that sort of thing. I think we've thought about it. We've like wondered about whether you can implement it. So I guess in practice, it has like a lot of recursive layers, but like actually the number of recursive layers I think is actually like 3 or 4 or something. So that part is not so bad. In terms of runtime, it does actually pretty well because basically what's happening is like almost all your insertions are only happening at the lowest level, and at the lowest level, you just have like an array of counters. You have some intervals, and you just like are receiving elements and like figuring out which interval it's in and incrementing that counter. So it's pretty good for runtime. It's unclear to me like how the constant factors shake out compared to say KLL or something. I think like if I were to wildly conjecture, I think it's probably comparable, and I'm not sure which one would edge out. Yeah.
clear, I mean, if you wanted, you could choose to only have the outer and the inner and have two levels of retrieval.
Yeah, you could.
That would already be.
Yeah, that would get log u. Yeah.
Is there any point in playing with the degree of the tree?
Yeah. So the trade-off there is that if you increase the degree of the tree, then like the number of non-empty nodes, the bound on the number of non-empty nodes increases proportionately to the degree, because right we bounded those by saying all their parents are full, and so in a tree of degree d, like the number of non-empty nodes is like can be up to d times the number of their parents.
Maybe you should put high degree nodes at the top and then have the degree decrease going down through.
That's possible. I think actually that turns out to be equivalent to increasing the capacity going down the levels. These like you can show. I think again, I'm not like I don't remember exactly, but I think these are essentially the same. And so we did try that. By itself, it doesn't work, but it's plausible that it could yield some insight on this algorithm.
What could you hope for with randomization?
All right, so this lower bound still goes through for randomized algorithms. So like in some sense, like if you squint and like say that both of these lower bounds are epsilon inverse words, then like in some sense it matches that lower bound. But I think in principle you could hope to improve this part of the bound with a randomized algorithm. Though again, you need some dependence on delta, so it wouldn't be like comparable. And the other thing is that like n would need to be much bigger than u for you to care about that. Yeah.
Just about that, so what is the parameter regime we should think of as that being interesting? Like the problem in general is like n much greater than like n much smaller than u, or like
I think various regimes can be interesting. I think I personally like tend to think of u as being like true to 64, but there are like applications where like maybe like the server latency example that I mentioned, right? Maybe each server has some millisecond latency between 1 and 999, and then like u is actually really small and n is huge. So I think all regimes like are potentially interesting, which is why I think this lower bound is relevant, because like there are I think real regimes where n is not like poly of u.
Thank you very much.